viewers. My name is Andrei Fedorov. I'm a researcher at the Institute of Continuous Medium Mechanics that's located in the city of Perm, Russia. My work is devoted to the numerical analysis of deformation of underground pipelines as a result of ground surface deflection. Underground pipelines can cross hundreds of kilometers of terrain with varying environmental and geotechnical conditions. Along certain sections, the pipeline may experience long-term and large-scale ground movement due to accumulated deformation caused by ground subsidence, porosity, sliding slopes, surface slopes, intervention of other structural objects such as rivers, tunnels, mine walking. Under such strong ground movements, the pipeline may become excessively deformed. In the area where pipelines are subject to compressive forces, deformations and faults of pipeline walls occur frequently. This results in progress of corrosion and leading to holes in pipeline walls. The examples of failures of steel pipelines in the mining areas you can see on the top of the slide, while the examples of failures of rigid pipelines buried within mining area are illustrated at the bottom. Horizontal deformations of soil can lead to significant increase in values of longitudinal stress in polyethylene gas pipelines. Buckling forces pushing the gas pipelines toward the surface, often blocking the natural gas flow. In order to assess the critical conditions of underground pipelines, it is necessary to know the values of pipeline stress and strain as a result of deformation processes in surrounding soil. The change in the relief of Earth's surface reflects the deformation processes in the soil mass. So it is necessary to establish the relationship between changes in the relief of Earth's surface and strength of pipelines in the soil. There are many options for remote sensing of relief of the Earth's surface by aerial and space vehicles and unmanned aerial vehicles. Remote sensing of Earth's surface allows us to detect changes in its topography, and our goal is to establish the relationship between the deformations of its surface and deformations of buried pipeline by using mathematical modeling. In the model under consideration, deformation processes in a soil mass okay? As a result of violation of its uniformity. Until the mechanism of appearance deformation occurs that natural processes, for example, appearances of cast cavities, and man-made processes associated with various underground works. Finite size so massive with cavity located at the depth of page is considered. Various forms of cavities are considered: semi-ellipse, ellipse, rectangle. For each shape of cavities, the relation of geometric parameters in cavity depth were varied. This made it possible to determine the dimensions of soil mass that ensure compliance with the variant of semi-infinite soil mass with similar cavity. Using the found soil dimensions, the constructed model is supplemented by pipeline embedded in soil mass. Different boundary conditions are considered on the contact surface between soil and pipelines, that is, dry friction conditions and ideal adhesion. The constructed model is supplemented by pipeline embedded in soil mass. On this slide, you can see dimensions of pipelines, material properties, and example of finite element mesh near pipeline. On this slide, you can see original field of longitudinal strain in pipeline. Strain transfer coefficient is the ratio of maximum longitudinal strains on the soil surface and maximum strain of pipeline. For these parameters and ideal adhesion conditions between pipeline and soil, strain transfer coefficient is 6.5. When we use dry friction conditions between soil and pipeline, strain transfer coefficient is 9.8. That means the deformation on the soil surface in 9.8 times bigger than maximum strains of the pipeline. The relative depth of cavity location is determined below which cavity shape no longer affects the strain transfer coefficient. On this slide, you can see the dependence of strain transfer coefficient on the eccentricity of elliptical cavity when the cavity volume is constant. In conclusion, I would like to say that a numerical modeling technique has been proposed to establish a relationship between ground surface strains and pipeline strains. For the model of finite size soil massive with pipeline embedded in massive, a three-dimensional problem of elasticity theory has been solved, taking into account friction on the contact surface between soil and pipeline. The possibility of obtaining the strain transfer coefficient, establishing the relationship between maximum strains on the ground surface and the maximum strains of pipelines embedded in certain depth in the soil mass, has been demonstrated. The relative depth of the cavity below its shape ceases to influence the strain transfer coefficient is determined. Thank you for your attention.